due dates, I kind of mapped out the rest of the summer here for us. I think. Where did we go? If I open all of them up. Okay. So today being the 22nd. I didn't put any due dates on anything that I opened up. Notice that I just took all the due dates off of all those first homeworks so that you could go back and fix things and work things out. And you can do that right up until you take the test. When you take the test, then I'll close those out, and we'll be done moving on to the next thing. That will be within this week or the very first 2 days or so of next week. So please tell me when you're going to take the exam and take it. Then, circular motion I have due the 28th, which I believe is Monday. Is that correct? No, Tuesday. So that's next Tuesday, the circular motion and gravitation homework will be done, will be due. We've already covered that chapter. There's a video posted, I believe. I think there's one that works. Just check to make sure. I think it's called 0620. No, it wouldn't be 0620. It would be 0613. And it would be called Phys 1410. Didn't like either of those. See if I can find my channel from here. I never can for some reason. I can never find my videos by searching this way. I guess I just have to sign in. If I can remember my password. Not bad on the first try. Okay, 6:13, there it is, 6:13, 6:15. So we've got videos for these things right here posted for these last two chapters. So make sure that you get started on those next sections as soon as you can get the test done. Due starting next Tuesday, so it'd be best if you could take the test this week and get started on the next homework, because after that, the work and energy homework is due the 1st of July, which is next Friday. Not this coming Friday, but the next one after that. And from now on, the homework is going to be due Tuesdays and Fridays, the day after we meet on Tuesday, and 2 days after we meet, which would be Friday. That gives you kind of an even, kind of a even spread of days between homework being due. 4 days between the Monday and Friday, the Tuesday and Friday, and 3 days between the Friday and Tuesday, or the other way around. 4 days between the Friday and Tuesday, whatever. Anyway, it gives you a better spread of days, I think, to get the homework done, and time to work on it after you've asked your questions or seen it worked on in class. So this new schedule also gives us just enough time to finish up the sections we need to finish, which are linear momentum, statics and torque, rotational motion, which is different than circular motion. And then we'll do fluid statics, fluid dynamics, and oscillations and waves, and then hearing. We're going to skip the thermodynamics portion of this since it is not required for either of your programs. If you're going into engineering or physics, you'll take the courses in thermodynamics at a later time. So that's kind of where we're at this point. As a reminder, really quick, let's go back to here. Let's see, as a reminder, in July, I will not be broadcasting from North Platte. In July on the, let's see, starting on the 11th and ending on the 25th, so the 11th, the 13th, the 18th, the 20th, and the 25th, I will be recording a lecture from California and posting it on YouTube. I mentioned this at the very beginning of the class because I will be gone to a conference in California. And you will still get your classes. You'll still get all the FaceTime you need with me, but I will be gone. Which also means we need to meet at least one more time before I leave to do labs. So probably the week of the 4th of July, maybe. The week before I leave, we meet to do some labs, and then we meet the last week before class ends to do some labs, and then we'll be done with the labs as well. How many labs did you guys finish the other day? 2, 3? 3 labs total? Yeah, that'll be perfect. And the ones you did are some of the longer labs, so 1 or 2, I think 2 of those I actually do, and I actually take 2 labs to complete, so you guys moved pretty quickly. All right. Any questions involving the schedule as it comes up here, as we're getting through here? Let's see, let me just count how many sections we have left. Make sure I've done this right. We have 1, 2, 3, 4, 5, 6, 7. According to our calendar, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 5 periods. Okay, so that's, yeah, I think we're there. So today, my plan is to go through any of the homework questions, for the exam again. We have essentially chapters 1 through 5, and I want to just take a look at and ask you if you have any questions. Look at the homeworks that have been done and the scores that you've gotten on them, any questions that you've had on them, so that we can check and see, and then check to make sure that you're understanding things. And then my plan is to give a short review, quick review of the 2 chapters that we've covered since we've been preparing for the exam. We covered those kind of early, so I'm going to just review them again so that you can get started on those homeworks as well. Get a lot of overlap when we have this short semester in the summer. So, all right, if we don't have more questions, let's go ahead and start looking at the homework. This is the homework from chapter 1, the nature of science. It looks like Chapter 9 gave some people some issues, so or not chapter 9, question 9. So let's take a look at it again. We have the volume of a sphere given by this formula, V equals 4/3 pi r cubed, where r is the radius. Compute the volume of a sphere with a radius of 877 picometers. And state your answer in units of meters cubed. This is a common trouble spot, these kind of calculation and conversion problems. So let's take a look at it really quick. Everybody that did the homework struggled with this one a little bit, so we might as well give it a go. Okay, so we have a sphere here. I'm going to start by drawing a picture like always. We've got a sphere, it's got a radius 877 picometers, right? And the volume of the sphere is given by 4/3 pi r cubed. This pen bleeds right through the paper, so I'm going to switch pens really quick. And they want us to calculate the volume in units meters cubed, so not picometers. Okay. Now, if you look up in your book or online what a picometer is, it will tell you that picometers are times 10 to the minus 12 kind of thing. So it ends up being 877 times 10 to the minus 12 meters is your actual measurement for that radius. So that's your R right there. And of course, we're just going to plug that in and we're going to cube it. Right? We're going to cube the 877. We're going to cube the 10 to the minus 12. And so if you cube R, you're going to get 877 cubed times 10 to the minus 12, also cubed, meters. Right? 10 to the minus 12 cubed is easy. What is it? When you take a power to a power, what do you do? What do you do to them? You multiply. So this ends up being 10 to the minus 36, right? So a very, very tiny number. And 877 cubed is something big. 877 is almost 1,000. And so if it was 1,000, it'd be 10 to the 3, so it'd be about 10 to the 9. Since it's not quite 1,000, it's probably a little bit more like 10 to the 8. But it's pretty close to that. And so we get some number kind of like 10 to the 8 times 10. And what happens if you multiply a 10 to the 8 times a 10 to the minus 36? How do you do multiplication of you have the same base with different powers? How do you do that multiplication? What's that? That's right, you add the powers. So in this case, r cubed is about equal to, it's not exactly equal to, because I've been estimating a bit here, but it's about equal to 10 to the 8 times 10 to the minus 36 meters. And if we do this multiplication, simple way, it just ends up being 10 to the 8 minus 36. You just add those two together, meters, right? Which ends up being 10 to the minus 28 meters. So that's my r cubed. And if I use this formula up here, it's 4/3 times pi times r cubed, and pi and 3 are about the same, so I'm going to cancel them out. This is not a good idea for you to do in your homework. You should probably do the calculations a little more cleanly so that staff and learning knows you got it right. But I'm going to essentially get 4 times this number, so it's going to be about 4 times 10 to the minus 28 meters, and that's an approximation, but you should get something in that range, something pretty close to that range for a number similar to 877 picometers. So that's the easiest way to do it. Some people will calculate everything in picometers, and then at the end they will convert to meters. But I would not recommend that, because your picometers cubed can get very confusing. It's very confusing to convert picometers cubed into meters cubed. So, and this is not meters, this is meters cubed, meters cubed, meters cubed. And so this is meters cubed, right? Sorry about that. But anyway, I would convert everything into meters first and then go through your calculations, rather than calculate first and then convert. It's much easier to convert first in almost every situation. Okay. $16 was another problem, student. There are a couple others in here that gave a little bit of trouble. Number 12, I think it is. Okay. 12. We have the sun shining on the United States, and you have 2.44 times 10 to the 3 kilojoules of energy reaching a square meter. So kilojoules per square meter, per meter squared, on the United States in 1 hour. That's per hour. So 2.44 times 10 to the what was it? 10 to the 3 kilojoules. Sorry, 2.44 times 10 to the 3 kilojoules per meter squared per hour on the United States. And we want to know how much solar energy reaches the entire states in per hour. How much total energy, solar energy reaches the entire United States per hour. So this is per meter of the United States, but the United States has, and they tell us right here, 9,158,960 kilometers cubed of area. So we need 2 kilometers squared, sorry, of area. So we need to figure this out. Well, converting kilometers squared to meters squared to kilometers squared is always a little bit difficult, so you gotta remember how it's done. If you have a square kilometer, this is 1 square kilometer. How many kilometers are on each side? Or how many meters are on each side? 1,000 meters on this side, right? 1,000 meters on this side. And to get the total number of square meters in here, you have to take 1,000 times 1,000, and you'll find out that 1 kilometer squared equals 1 million, or 10 to the 6 meters squared. Right? So 1 square kilometer is 1 million square meters. So if you have 9 million square meters here, 9 million square kilometers here, you have to multiply this number by another million, by another 10 to the 6 to get the square meters in the United States. So this is 9 times 10 to the 6 already. If you multiply it by another 10 to the 6, you get 9 times 10 to the 12. So the actual area of the United States is 9.158 times 10 to the 12, instead of this 10 to the 6 here. It's times 10 to the 12 meters squared. And then you can multiply these two numbers together. And if you multiply them together, the meter squareds are going to cancel, and you'll get kilojoules per hour. And that'll tell you how much energy per hour is reaching the United States as a whole. It's going to end up being a big number. $13 was another trouble spot. Because concerning the speed of light, speed of light in a vacuum, 2.998 times 10 to the 8 meters per second. We call that C. And they want to know what is the speed in kilometers per hour, right? So if you have meters per second, you want to convert to kilometers per hour, you need to use a conversion. The conversion factor is going to change the meters to kilometers, and it's going to have to be kilometers per meter, and it's going to be 1 kilometer per 1,000 meters, right? And then to change seconds, right? You have meters per second. You're going to want to replace the seconds with hours, so you put the hours in the bottom because you're replacing the seconds. And then you have to put however many seconds there are in an hour on top, 3,600 seconds. So the seconds cancel, the meters cancel, and you're left here with kilometers per hour. Remember how to do conversions. So your conversion factor for this one would be 1 times 3600 divided by 1000. It'd be, that'd be your conversion. 36 over 10 essentially. So 3600 over 1000. All right. So don't forget conversions. Convert at the beginning, then do the problem. Second to last one on this one, another conversion. No, second to last one on this one was an uncertainty thing here. So they have beats per minute of a heart, 127 plus or minus 6 beats per minute. They want to know what is the uncertainty and what is the percent uncertainty. So the uncertainty is this number right here, 6. That's your uncertainty. The percent uncertainty is you take the 6 and you divide it by 127, and that will give you a decimal point, a decimal number, like point. In this case, it's going to be, what is that? 0.02-ish. No, it's going to be more than that. But anyway, it's going to be some amount, I think 0.03 maybe. But anyway, about that, and then you multiply that by 100 to get the percent, so it's going to end up being a 3% uncertainty there. And then the last problem that gave anybody trouble, gave you guys trouble, was 16. Let's see if it lets me open it. So far it's not. Here we go. So in these ones were all the problems where we're doing scientific notation math, and we already did a little bit of that, so I'm not going to do any more. Okay, so that's the Chapter 1 homework review. Let's move on to Chapter 2 really quick. Okay, so on this one, they're asking you, at which lettered point is the object moving the slowest? And this is a position versus time graph. So this tells you where you are in the X or Y direction or something, in some direction. So the further away you get from the horizontal axis, the further you are away from the 0 point. And this is time along this axis, so this is happening in time. Well, speed on a graph like this of a position versus time is related to what part of the graph? What part of this graph tells us how fast the car is going, or whatever is going, whatever is going? Well, let me give you a clue. As we're moving along here from the time equals 0 to point A, we are getting there in a certain amount of time. That would be on this axis, on the y-axis here. Or sorry, on the x-axis. So we take about this little bit of amount of time to get to point A. But we take about twice as much time to get to point B, even though point B is only twice as far away as A. It didn't take us the same amount of time to get to B, it took us twice as long to get to B. Which time were we going slower? The first one or the second one? The second one, right? So what part of the graph is telling us how fast we're going? Well, time combined with how far we go, and what part of the graph do we call that? Rise over run. The slope, right? The slope of the position time graph tells you the velocity. So this is actually telling us, this very steep slope right here is telling us that we went really fast. But then as it's not so steep here, we're going slower. And in fact, at point B, how fast are we going? What's the slope at point B? 0. So how fast are we going at point B? And then after point B, from point B to point C, what do we know about our velocity? What's different? The slope is going down, which is a negative slope, which means which direction are we going? Back the way we came, which means we turned around. Point B is called a turning point for that reason, because we've turned around and we're now going the opposite direction. And at which point on this graph are we going the slowest? Well, at which point on this graph are we going not at all? B, so that has to be the slowest, right? Slowest is stopped, right? At which letter point is the object moving the fastest in this graph, would you guess? I would say D. It's pretty steep there. A is pretty close to it, but I would say that D is probably a little more steep. So it's probably the fastest. I have a hard time saying that for sure. But. Next one. Here they give us a graph of the velocity. So now they're telling us the velocity, and we want to figure out what the position is of this thing. So the velocity of this thing is at -2, and they tell us that it starts at time equals 0. There's a mailbox 1 meter in front of of John, the guy rollerblading. I was trying to figure out his name. So at time equals 0, there's a mailbox 1 meter in front of him, and we're going to say that the mailbox is the 0 location. So if he's starting 1 meter behind the mailbox, and the mailbox is at 0, where does this graph need to start? -1, so we put it at -1 to start, right? So he's starting at -1, and what's he doing from time equals 0 to time equals 1 right here? He's moving at a speed of what? A velocity of what? -2, so what is the slope going to look like here? It's going to be negative, right? And in 1 second, he will go how far? 2 meters. So he's going to go 1 meter, 2 meters, so he's going to get all the way to here in 1 second, because he goes 1 second at 2 meters per second. And then what does he do for the next second? Nothing. His speed doesn't change. So what happens to his position? His position doesn't change either, right? If your speed doesn't change, you don't go anywhere, right? And then what happens to his speed after that? It goes to positive 2 meters per second. So the slope here is going to be positive, and every second he's going to go 2 meters. So here's a second, he's going to move up 2 meters. Another second, he'll move up another 2 meters. Another second, he'll move up another 2 meters. And there you go. And now you can see that the slope of the position, it's a -2 slope here, is the velocity. -2 slope, -2. 0 slope, 0. +2 slope, +2 velocity. All right? It's very important to learn how to understand graphical representations of information, especially in the sciences, but really just about anywhere. Don't forget to go back to your homework and rework these problems, because these problems that you maybe struggled with before are going to be you're going to need to understand them. So go back and rework these homework assignments. Try to get these right for the test, and then take the test right away, so that it's fresh in your mind. Similar problem here, except we're going to make the velocity graph, and this is the position. So remember, velocity is the slope of the position, right? And right here it says our position starts off not at 0, because the position's on the y-axis. It starts off at some distance above this y-axis. But we don't really care what our position is when we're graphing the velocity. We just want to know the slope is 0, right? So the slope is upward. It looks like it's going up at a very slight kind of way, in a very slight way, which means we're moving forward, but the slope is not changing. So we have a constant velocity, and it's positive because it's upward. So we're going to go ahead and change this and see if we can change it. There we go. So it's got some positive slope up here, and then it changes abruptly and becomes negative, but it's much steeper as a negative. So it's got to be maybe twice as steep in the negative direction after that. This was that great word problem that you had to solve by writing down a bunch of information about two people, right? So let's go ahead and try this one really quick. We have to try to be done here a little bit earlier than normal because I've got to go and pick up my car at 5:30, but we'll still try to make use of all the time we have. So we have a cafe, and I'm eating lunch at my cafe. And your friend called, says he wants to meet you. He's calling from a city 135 miles away. So between here and the city that your friend is in, right? Oh, I'm sorry. Source. Okay. So here's my cafe, here's my city, 135 miles away. Right? He wants to meet somewhere in between, so we're going to meet somewhere in between here in some mysterious location in between these two places. Right? He's going to start driving right away, but you need 27 minutes to finish your lunch. And so he's going to drive some distance, we don't know how far yet, but we do know the time difference is going to, we know what the time difference is going to be. Whatever time he takes to drive, my time is going to be his time minus 27 minutes, because I'm going to have to take some time to finish my lunch. So I'm going to write down that information. This is the time my friend travels, my time is going to be his time minus 27 minutes. Okay? My friend is going to drive at a speed of 75 miles per hour. I'm going to drive at 55 miles per hour, so speed, this would be speed 2, I'll call this time 2. This will be time 1 equals time 2 minus 27. This will be speed 1 equals 55 miles per hour. So I'm just writing down information right now. We want to know how long your friend will be driving before he meets you. So we want to know T2. T2 is the thing we want to know, how long he's going to be driving before he meets me, right? We want to know what T2 is, that's the first thing. And then then we want to know how far you will have traveled by the time you meet him. We'll figure that one out later. But essentially we've got everything we need at this point. It's just a matter of understanding how to put it together. So one other piece of information that we didn't quite write down yet is that at this place that we meet in between somewhere, we're going to have two distances. We're going to have the distance that I travel, which I'll call distance 1, and then I'll have the distance that my friend travels, which is distance 2, and I'll let distance 2, let's see, I'll let distance 2 equal 135 miles, which is the total distance, minus distance 1, because it'll be the total minus whatever I travel, right? So I'm just going to write that down. And this becomes now just a problem of writing down two definitions. The definition of the speed. The speed that someone travels is equal to the distance divided by the time. So speed 1, which is the speed that I traveled, is equal to distance 1, d1, divided by t1. And speed 2 is equal to d2 over t2. It's really quite simple. These two equations are always going to be true, and we've written down some things that are going to connect the two together. So I write down everything I know so far, and now I'm going to write down other things that I know. I'm going to make some substitutions. For example, for speed 1, I'm going to write 55 miles per hour. And for distance 1, I'm just going to write distance 1 since I don't know anything else about that. But for time 1, I'm going to write it as time 2 minus 27 minutes. So that's going to be t2 minus 27 minutes. Okay. And then for my other one, right here, I know that speed 2 is 75 miles per hour. And I know distance 2 has this relationship 135 miles minus distance 1. And then I divide by t2, which again I don't know yet. So now I have these two equations to work with. The great thing is in these two equations, I have some things that are similar. I have a d1 in both equations. I have a t2 in both equations. And those are my only variables. And essentially, these two equations become they become like two equations, two unknowns that I can solve for both variables. And each of these variables is one of them I want to know. t2 is part A. d1 is part B. Right? I did that on purpose. I left those in the equations because I wanted to know them. And so what I can do is I can solve this equation, for example, which is fairly simple, or either one really. I can solve one of these equations for one of the variables. If I take this one on the left, I can just multiply by t2 minus 27 minutes. And you do need to make a conversion here. I would divide the 27 minutes by 60 minutes so that you get a fraction of an hour, so that you have the same kind of units with the miles per hour. And I would, that will help you a lot. But anyway, that will not only help you a lot, it'll help you get the answer right. But if you multiply both sides of this equation by this t2 minus 27 over 60 hours, then you will get expression for distance 1 that you can plug in over here. And then you can solve both of these equations then you can solve these equations. What this is going to give you when you do this is it's going to give you an equation that has a bunch of numbers and t2s in it. So you can solve for t2. Solve for t2. Once you solve for t2, then you can plug t2 into either one of these equations and solve for d1. And then you'll be done with that problem. But this is how these kinds of problems are often solved, almost always solved. You write down the things you know, you write down equations that have the things that you know in them, and also have the things that you want to know in them. Then you plug in the things you know, and you solve for the things you don't know by doing multiple equation solving, plugging one of them to the other, whatever you want to use, whatever method you want to use to solve multiple equations with multiple unknowns. Okay, so here we have another problem with a graph. Let's go back to our computer here. So here we have a public transportation bus. We have a position versus time graph. And they want to know the average speed and the average velocity of the bus between points 1 and 4. Of the two, the average velocity is actually easier. All you do for the average velocity is it's the definition. The average velocity is the final position minus the initial position over the time. So the time here is 3 hours total between point 1 and 4. That one's easy. Then the 4 is the final position, so it's at 35 kilometers. The initial position is 40, so you take 35 minus 40, you get minus 5 So you put that in your equation for the average velocity, you get minus 5 kilometers divided by 3 hours. And that's pretty simple. Pretty simple stuff. Turns out to be, I think, 1.66 kilometers per hour or something. Then you have to convert to meters per second. So that's the average velocity. For the average speed, it's a little bit different. You actually have to calculate how far it goes, total. So you calculate the entire distance it's traveling. So from point 1 to point 2, it travels from 40 to 15, so it goes 25 kilometers. And then from 2 to 3, it goes from 15 to 30, so that's another 15 kilometers for a total of 40. And then from 3 to 4, it goes another 5 kilometers, it looks like. So it's 45 kilometers total that it travels, and it takes it 3 hours to do it. So the speed, the average speed, is 45 kilometers divided by 3 hours. It's the total distance divided by the time. And that's 45 divided by 3, so it's 15 meters per second. So its average velocity was negative 1.66 meters per second. But its average speed was 15 kilometers per hour. Because the velocity doesn't care what path you took to get where you got to. Whereas the distance just follows the path. And then do the same thing through from points 2 to 5. Okay, moving sidewalk. An initial velocity on the moving sidewalk of 2 meters per second. And she experiences acceleration. And this graph here is the acceleration graph. And this should be a little bit, you should understand a little bit more of this, I think, after you've done the lab, hopefully. But the acceleration graph tells you how the velocity is changing, right? And we're starting at 2 meters per second. If we're starting at plus 2 meters per second, we need to go ahead and put our graph starting point at 2 meters per second. Then we look here and we see that the acceleration is positive 2 meters per second squared. So what's going to happen to the velocity graph? It's going to increase by 2 for that first second. And then it goes down to a 1 meter per second squared. What's going to happen now? It's going to increase, but not as much as before, not as steeply, right? And then it goes to 0, so what's going to happen to velocity? Stay the same. And then it goes to a negative 3 acceleration. This thing is going to decrease by 3 over the next second, right? And then it goes to 0, so this does what? Doesn't change, right? The rocket sled again. Okay, 282 meters per second top speed, 5 seconds. Let's see. So he accelerated from rest to a top speed of 282 meters per second in 5 seconds. And then he was brought back to rest, where he stopped in only 1.4 seconds. And I calculate his acceleration. So his acceleration, you take the 282 meters per second, which is his final speed, subtract his initial speed, which is 0, divide by the change in time, which is 5 seconds, and you get an acceleration. For the deceleration, you're going to take his final speed, which is 0, and you're going to subtract off his initial speed, which was 282 meters per second. You divide by the time, 1.4 seconds once more. To calculate in multiples of g, both of these have to be calculated in multiples of g. So each one of these accelerations that you calculate is going to come out in meters per second squared, and you just divide by 9.8 to calculate it in multiples of g. And they don't use negatives or positives, I don't think, on that one. It's just always positives. Motionless test car accelerated in 8.3 seconds. So again, here they're going to have you calculating accelerations. A person is initially driving a car east down a straight road. Magnitude of the instantaneous acceleration is increasing with time, and the direction of the acceleration is always to the west. So if the acceleration is increasing to the west and the car is traveling east, what's happening in the speed of the car? It's going to decrease because it's going one way and being accelerated another way, right? So it's going to decrease the car's speed, right? And then eventually it'll stop the car and start increasing the car's speed, but in what? The other direction, right? This problem is kind of like having a car that has run out of gas and all of a sudden the engine stops, but there's a wind blowing and your brakes don't work. And you're driving it on ice so that there's no friction. So what happens at first? At first you keep going forward, but the wind that's blowing in your face is going to slow you down and then stop you. But as the wind keeps blowing, you keep accelerating back in the same direction, you're going to speed up, but in the other direction. And here it doesn't say velocity, it says speed. So speeding up is a perfectly valid answer. A person initially driving a car east down a straight road. The acceleration is decreasing with time, but the direction of the acceleration is always to the east. Let's see. So the acceleration is decreasing. The last time said that the acceleration is increasing, right? So if the acceleration is decreasing with time and it's going against you, then you're going to, if it's decreasing with time, eventually it'll become zero. That means you're going to slow down a little bit and a little bit and a little bit, but you're going to slow down less and less and less until it becomes zero, and then finally, let's see, if the acceleration keeps decreasing, then it'll be going the other direction still, essentially be, let's see. I think that one, speed of the car. I'm not sure about this one. Oh, sorry. I misunderstood. In this one it says the person initially driving a car down a straight road. The instantaneous acceleration is decreasing with time, but it's in the same direction that he's going because it's east acceleration and the car is driving east. So the last one, the car was driving one way, the acceleration was in the other way. But this one, the acceleration is one way and the car is driving that way. So it's being accelerated, but that acceleration is decreasing, but it still will go faster and faster until the acceleration stops, until it becomes zero. So this one will increase because it's accelerating, but then it will actually stop. It'll stop accelerating the car, and the car will then slow down after that. So this one has to be increasing, then decreasing. In this one, a person is initially driving a car east down a straight road. Magnitude of the instantaneous acceleration remains constant with time. Direction acceleration is always to the west, so it's always to the west. Car is driving east. And that's going to be the same thing as the first one. It's going to decrease and then increase. It's just the opposite direction. I don't like those questions. I think that they've put some questions in here that I didn't put in originally, so I better go back and check that. So in this one, you actually have to use a kinematic equation because you have this airplane that is moving with an initial velocity and it travels a further distance with a particular acceleration. No, for a particular time. It has an initial velocity, a final velocity, and a distance that it travels in that time. And you're supposed to calculate the plane's acceleration. You use a kinematic equation for that. Not hard to do, but then you have to use another kinematic equation to figure out the time that goes by. Essentially just two kinematic equations. One of them that has distance and initial and final velocity, and then it also has the acceleration in it, I think of the equation. And then one that has those things and the time in it, so that you can calculate the time from those things. Everybody missed this one, looks like. A mamba snake. So in this one, let's go ahead and take a look at this one a little more closely, and then we'll take a little bit of a break. So I'm getting tired here. Come back to it. So in this one, you have a snake that has a length of 2.97 meters, top speed 8.79 meters per second, and the snake accelerates at 6.5 meters per second squared. How much time does it take the snake to reach its top speed? Well, we have an acceleration and we have a top speed, right? Sorry. Thought I was doing this. Oh. It's not over here, okay. So essentially I've just written down these things. I've written down the length of the snake, the top speed of the snake, and the acceleration of the snake. If you have an acceleration and a top speed, that essentially is you've got this equation here. The acceleration is the velocity final minus velocity initial over the change in time, right? And we want to find the change in time. So you plug in this as your final velocity, your initial velocity being 0, your acceleration is known, and you calculate the time. Pretty simple. And then you want to know how far does the snake travel in that time. The snake travel, if you want to find out how far something travels and you know the acceleration and you know the time, you can actually calculate the distance. We have an equation for that as well. It's one of the kinematic equations. Then we will ask, when the snake has reached this top speed, has its tail gone past the mongoose? And essentially compare your distance traveled from this one, your delta x, compare that with the length of the snake. And if delta x is longer than the length of the snake, then you're good to go. If not, then the snake has been getting eaten by the mongoose. And the rest of these problems are all kinematic equations problems. If you've not ever seen this particular phenomenon, you should go watch some nature videos. They're kind of cool. Foxes, snow foxes, hunt by jumping into the air and diving into the snow. It helps them to burrow into rabbit holes and things. But anyway, so if a fox jumps into the air and it jumps a height of 0.93 meters, that's just 93 centimeters, then we can essentially say that its initial height, its initial y0 is 0.93 meters, and the speed that it reaches the ground can be calculated, which would be the same speed that it takes off with, because the speed that it takes off with and the speed that it lands with are equal. So you can calculate both of those using kinematic equations. Because we know the acceleration is going to be gravity, 9.8 meters per second squared, and we know the distance that it's going to travel in that acceleration. And we know that its initial velocity up here. Sorry, I forgot to do that. Sorry. So here's our picture. Sorry for that. Here's our picture. We have the 9.3 meters that we're starting with. That's our initial y. And then our acceleration is going to be gravity, right? And our initial velocity at the top there is going to be 0. We can calculate our final velocity from the kinematic equations, right? And that's one of the things they want to know. The other thing they want to know is how long is the fox in the air? So you calculate how long it takes the fox to fall from here to the ground. You have to double that. So time equals 2 times it takes to fall down, right? Because it has to jump up as well, and then you're good to go with that problem. So this one is, let's answer your question. So the acceleration of the runner during segment 1 is, well, he's not changing his velocity, so what's his acceleration? 0, right? So how do you calculate average acceleration between 2 points? Between 0.4 and 6, for example? If you're going to calculate the average acceleration between 0.4 and 6, you essentially draw a line between 0.4 and 6 and calculate the slope. Or you take the number of boxes that it rises, which is 1, 2, 3, 3, negative 3 because you're going down, and then 1, 2, 3, 4, 5, 6, 7. So it ends up being negative 3 over 7, rise over run. Good question. I always forget. So if we're doing the average acceleration on a velocity graph, remember acceleration is the slope of the velocity, but if you're going between 0.4 and 6 like we are here, and there's this hitch where it goes down to 5 and back up to 6, acceleration just goes point to point for average. So you just draw a line between 4 and 6 and calculate that slope, which means you essentially just take how far it goes up or down. If it's down, it's negative, so it's 3 down, and 1, 2, 3, 4, 5, 6, 7 over. So it's negative 3/7 meters per second squared of acceleration. Exactly. And, they're actually doing the average acceleration at 4, during segment 4. Okay, so that was between 4 and 6, but if you want to know what their acceleration is at, oh, so this is segment 4 here. So this one you just do that, you just do the slope on segment 4, because segment 4 is not between 2 points, it is just the segment. So you just do the rise over run, 1, 2, 3, 1, 2, 3. So it's 1 essentially, and then the other one is 1/4 it looks like, rise over run. Just the slope. So this is another kinematic equation problem. All right? You're going to have one or more equations with the stuff and solve them. This is also one of those. I mean, these last ones are just kinematic equations problems. So I'm going to take a little bit of a break, just a few minutes, and then we'll come back and we'll try to review as much as we can of the next couple chapters before we're done today. Okay. All right, let's see where we can get to now. Let's go to a 2D kinematics and see how we're looking on that one. Oh, yeah. Unsuspecting bird. Alright, so this bird apparently is coasting along in this easterly direction. So moving along this way, 4 miles per hour. A wind from the south imparts a constant acceleration, A, of 0.4 meters per second squared. Acceleration from the wind lasts for a time, 2.9 seconds. I want to find the birds so we want to find the magnitude and direction of the bird's displacement during this time. Okay. So first of all, we want to convert this thing into meters per second. And once we do that, then this problem is going to have a couple of things that we're going to have to do to it. First of all, we want to split things into the x and the y dimension, right? So if this is my coordinate system x and y, then it has an initial velocity in the x direction of whatever it is. Let's say, I don't know what this is going to be exactly, but let's say that it ends up being about 1.5 meters per second. It's going to be close to that, 4 miles per hour. So it's going to have a plus 1.5 meters per second initial velocity in the x direction. The final velocity in the x direction, which I'll just call Vx, I don't know. I'm just going to put a question mark. I don't know what it's going to be. Actually, I do know what it's going to be, don't I? Don't I? What is it?
Same.
It'll be the same, right? Because our velocity is in the y direction. Isn't that correct? Yeah. So our velocity in the y direction. So our final velocity is 1.5 meters per second. So we know that too, right? Good. So y direction. Initial velocity in the y direction is what? 0, because it's not moving in the y direction when we start. 0 meters per second. And then the final velocity in the y direction, which I'll just call Vy, that thing I don't know yet. However, I do know the acceleration in the x direction is what? 0. And the acceleration in the y direction is 0.4 meters per second squared. And those signs are all correct, positives and everything. I also know that the delta t is 2.9 seconds. So now I can take the stuff, the information in the y direction can be used to calculate the final velocity in the y direction. And since the velocity final in the x direction is already known, I can use the final velocity in the x direction and the final velocity in the y direction to get the final velocity overall, using Pythagorean theorem once I solve this one, right? How am I going to solve this one? Well, it's pretty simple. It's just the definition of acceleration in the y direction is going to equal the final velocity in the y direction minus the initial velocity in the y direction all over delta t. We already know that the initial velocity in the y direction is 0, We know the delta t is 2.9, and we know the acceleration is 0.4. So all you have to do is solve for this one. Sorry? Oh yeah, we need this one. We know this one, we need to solve for this one, right? So then we solve for this one. Once we've got that one, we put it over here in the Pythagorean theorem, and we'll use the Vx and the Vy to get the final velocity total. And then that V total we'll use with the time again to figure out how far it went at this angular direction. And that will tell us how far it goes. They want to know that. They want to know the magnitude of the displacement, which is r. So that vector would be r. And then they want to know the angle, which you can also get tangent theta equals Vy over Vx, right? Or the inverse tangent of Vy over Vx equals theta. That's how you do that problem. The turtle ambers leisurely, as turtles tend to do. Goes from one point to another point to another, does it in 31 seconds, components of magnitude. Okay, this one is most easily done if you just map it out. Alright? X, Y. So the turtle goes, we start R1, it moves from a location, so we'll call this location the origin. And that R1 in the x direction is 1.61 meters, so it goes R1 in the x direction is 1.61 meters. And then RY1 is, R1y is negative 2.71. That means that this point down here is going to be 1.61, negative 2.71, right? And then it goes from this position to another position, and they tell you the Rx and RY of that one. And they want to know a total, in the end, they want it takes 331 seconds to complete this thing. What are the components and magnitudes of the turtle's average velocity in meters per second? Well, if this is position, right, then we're essentially going to, and we're going to be going two other places. The other places are 3.03 meters, so it goes this way, 3.03 meters, and then it goes R2y negative 4.63. So to find its end point here, you add these two x's. You add R1x plus R2x, comma R1y plus R2y, right? And you'll get the final point where this thing is at. If you know the final point where it's at, then you know the total distance it has traveled, or the total displacement has traveled, just by using the Pythagorean theorem with these final 2 points. Square them, add them together, take the square root. That'll tell you the total displacement. You divide that by the total time, and that gives you the average velocity of meters per second. And they actually want it in the y and the x, so you actually just do those separately. You don't have to use Pythagorean theorem. You just take this r combined, divided by the time, this r combined, divided by the time, and you'll get the velocities in the x and y. And then, to get the average, you use the Pythagorean theorem there. But it's pretty straightforward. Yes. This is another problem of, so this is problem 11 in this homework, 2D kinematics. We have three vectors on your axes like this, an A with angle alpha, B, this angle beta, and a C straight down, right? And they want you to, they tell you what the angles are. They tell you the vector C has a magnitude, 27 meters. It's right on the y-axis. And A and B have these angles. Alpha is 44.9 degrees, and beta equals 27.2 degrees. And then they tell us that A plus B plus C equals 0. And that also is going to tell us something else, because this is two dimensions. We're going to do this in x and y. And that tells us that A sub x plus B sub x plus C sub x equals 0. And it also tells us A sub y plus B sub y plus C sub y equals 0. The interesting thing about that is that the C vector has no x component, right? It's only in the y direction. So if we go back here, we can say that C of x equals 0, and that tells us that A sub x has to equal B sub x. So the x components of A and B have to be equal to each other. Well, equal and opposite. It has to be A sub x equals minus B sub x. So then immediately we can say that A, the vector A times its angle times the cosine of its angle, so this would be A sub x right here. So A sub x equals A times the cosine, 44.9. So that means that A times the cosine, 44.9, has to equal negative B, and that one's also a cosine of 27.2. Has to equal that right there. So that gives us a relationship between A and B, because these two are numbers. We'll have a relationship between A and B. That's great. We can use that. And then over here, we know that C sub y, since it's all in the y direction, they've given us that number. It's 27, whatever it is. 27? Yeah, 27 meters. Oops. 27 meters. A sub y is going to be A sine 44.9. B sub y is going to equal plus B sine 27.2. This is not very good. Not written very well. So it's going to be A sine 44.9 plus B sine 27.2, and then the C sub y is just the 27 meters. And that has to equal 0. And again, this is a relationship here. This one's going to end up saying that A is equal to negative cosine 27.2 over cosine 44.9. That's just a number times B, right? So you can plug this one into this one and solve for the B's. And then once you have the B's, you can solve for the A's. Once you have the B's and the A's, then you're done with the problem. And then there's the classic problem of the pool table. This is in problem 18, looks like. You have the pool table, and you're hitting the ball off the edge of the table and it falls to the ground. And the distance here is given, it's 0.810. The distance here is that it flies is given as 4.35 meters. And essentially what you're trying to calculate is the initial velocity of the ball after you hit it. You hit it here, you want to know what this initial velocity is here. How do you do it from this information? Well, it turns out that you do it from this half of the problem. You treat this half of the problem as a ball that is just falling straight down 0.810 meters in the time that is given. And they tell us the time that is given, or do they tell us the time? No, we're going to calculate the time. Yeah, we're going to calculate the time because we can. Because the distance, when the ball falls, it's falling in gravity. It has, so in this y direction, in our y direction calculation, we have the distance, the delta y, the change in y, it's going to fall from 0.810 meters down to 0, so that's going to be a delta y of negative 0.810 meters. It's going to fall from that downward. And then we know the acceleration is g, which is negative 9.8 meters per second squared. We can use these two numbers to calculate the time that it takes for it to fall. Once you've calculated that time in seconds, whatever it is, then you go to the x portion of this problem, which is how fast was that ball going in the first place. As it goes off the table, it travels 4.35 meters along the ground, and it does it in how much time? Well, whatever time we calculated here. And then our initial speed is equal to the 4.35 meters divided by that initial time, that change in time that we calculated. And that gives your initial velocity. They also want you to calculate the speed that the ball hits the ground with. Well, to do that, you have to calculate how fast it's moving downward because it fell, and then add it using Pythagorean's theorem to this speed in the x direction. But remember, this horizontal distance that it travels is independent of the vertical distance. So you can just use that horizontal distance with the time to calculate the horizontal velocity of the ball initially. Okay, I've got time for one more good problem here. We'll do this classic problem of throwing a ball off a roof to calculate the height of the roof. Nobody got this one, so we'll work through it really quick. Again, it comes down to breaking a problem down into parts. So we have a roof here, and we're standing above the roof 2 meters. Because of our height and the height of our arm as we throw the ball. And we throw this ball at 32.1 meters per second because we know that's how fast we can throw a ball. And we throw it at some angle, we don't know what, but we do know that it comes back down to the height that we threw it at in 0.710 seconds, and then it falls all the way to the ground. And then the ball lands 129 meters from here. So this distance here is 129 meters. Right? So the best thing to do is to split this up into parts once again. So I'm going to split it up from the ball leaving my hand to coming back to the height of my hand, and then the ball falling at that point to the ground. In this first part of the problem, what I'm going to try to do is calculate how fast I threw the ball. Or not necessarily how fast I threw the ball. I know how fast I threw the ball, but I want to know what angle I threw the ball at and how high it went above the ground. I'm going to use this information to do that. And again, you're always going to split the problem into x's and y's. So I'm going to have an x, I'm going to have a y. And usually the y direction is going to tell me something about the time, and the x direction is going to give me some other information. But I do know, first of all, that I have this angle theta that I threw the ball at. That's one thing that I need to figure out. And so I'm going to try to figure that one out. And I know that I have this 32.1 meters per second of overall speed at that angle. So I've got 32.1 meters per second of speed at the angle of theta. And so my x velocity of the ball is going to be 32.1 times the cosine of theta meters per second. And my velocity in the y direction, therefore, will be 32.1 sine of theta. Right? That'll be my initial velocity in the x, my initial velocity in the y. That'll also be my final velocity in the x, because it's not going to change. Cosine theta. My final velocity in the y, I don't know. That's going to be accelerated by gravity quite a bit. Well, for the first half of the problem, I do know, because it's going to be the same as it was, the same going up as it was going down. But what I really want to do is actually just look at this problem from the beginning to the top of its movement, because then I know my final velocity is 0 at the top of that movement, because it's a turning point. It turns around at that point. That's going to help me. Only doing the first half of the upward throw, just doing this upward part of the throw, velocity initial being this 32.1 meters per second, velocity final being 0 at the top, that's going to help me a ton. But that means that I also have to change the time that goes by, because it was 0.710. I have to change that to 0.355, which is half. So I have a delta t of 0.355 meters per second, or not meters per second, seconds. And that will give me a total time of 0.710 there. Now I have initial velocity, a final velocity, a delta time, but I also know gravity. I know the acceleration is equal to negative 9.8 meters per second squared. That's going to help me because I know now everything to calculate theta right here. If I take the equation for acceleration, it tells me the acceleration is equal to velocity final, 32.1 times sine of theta, minus velocity initial, my velocity final is 0, so it's 0 minus velocity initial, minus 31, and then divide by the time, which is 0.355 seconds, and that has to equal my acceleration, which is negative 9.8. Negative 9.8, there we go. And all I have to do now is solve this problem. I end up taking negative 9.8, dividing by negative 32.1, and that just gives me a number. I multiply by 0.355 seconds, and that's going to give me the sine of theta. And then I can take the inverse sine of both sides and solve for theta. Once I know that angle, then I can do all kinds of things. Once I know that angle, for example, I can go back and calculate the initial velocity in the y direction, and then I can use another kinematic equation to calculate how much time or how much distance this thing is going to travel all the way through its motion. But probably the most valuable thing I can do is use this angle over here with the velocity in the x direction, and I can calculate the total time that the ball was in the air, because it goes 129 meters at this speed right here. So if I take this 129 meters divided by this speed using the angle that I calculate down here, then I will get the total time elapsed. And then I can use that total time to calculate how high the building is, because I know how long it takes. I know how, because I will know, what will I know? Oh, I will know the y, I know the initial y velocity, I know the y acceleration. And if I know the initial y velocity and the y acceleration, and I can count, and then I can, and what else do I need to know? That, the acceleration, the y velocity, I know the total time, so I'll know the time, then I can calculate the distance that it travels in the y direction, and then I'll know the height of the building as well. So, and then for that one, you just use the second half. Just use the initial velocity here, and the total time minus 0.71 seconds here, and you'll get the following time from here to here. Once you know the total time from the x, you can just take those two and subtract them, and then you can calculate the height of the building from another kinematic equation. That problem is several steps long and has a difficulty of 2, so it's certainly not an easy one. Okay, The other problems that anyone struggled with are really pretty much the same as this one we just did. And the key to these problems is almost always the same kind of thing. You need to set up the equation, set up all the stuff that you know in X and Y separately. And from one of them, you should be able to calculate something that you can use in the other one to get what you need. And that's usually what it is. And usually in the Y one, you're going to get some kind of time, or in this case, we got an angle. But the Y one is often very good for that because you already know the acceleration. The Y direction is negative g. So you have an extra piece of information in the Y direction, often. Sometimes they give you enough information that you can use the X direction directly to solve the problem and be done. But usually you're using one direction, one of the dimensions, to solve for something that you're going to use in the other dimension with a different kinematic equation. And then you're going to be able to solve the problem. And sometimes you have to go back and forth a couple of times, using one to solve for something in the other, to solve for something in the other, and to solve for something in the other. It's just a matter of never giving up on that and having those kinematic equations in front of you. I highly recommend that you have those kinematic equations in front of you when you're doing these problems. Don't go searching for them. Have them in front of you. Have your cheat sheet in front of you. Have your book open to that or whatever. If you have to go searching for them, your brain will not think of them when you need them. It won't think to use them. So have your equations out and ready to use. Let's see if we can maybe do a little bit of review on one more thing really quick. Something on forces. A little bit of dynamics here for a little bit. Okay, so there's a question in the dynamics chapter. You have a cube on top of another cube, and they're falling in free fall. Ignoring any air resistance, what's the magnitude of the normal force with which the bottom cube is acting on the top cube? The question that you have to really ask yourself is the bottom cube preventing the top cube from falling if they're both falling at the same rate? It is not. So what is the force? It's a zero normal force, right? So that's kind of a trick question. And this one is a classic. Physicists love. It's number 22, where you have the bar holding a package up on a ramp. So let's do that one really quickly. I'll just give you the basics of how to do that one. And then we got a jet. So we've got our package on the ramp, and it's a frictionless ramp, so if you let it go, it would just slide down. And we've got some angle theta down here that they give us, whatever it is, they give us the mass and whatever else. Then they apply a force like this, right? We need to set up this problem so we can solve for all the forces. First of all, we draw our free body diagram. So here's my free body right here. That's the point that represents the box. And it has forces acting on it from lots of different directions. First of all, it has this force this direction. And it has the weight, so this is the force F. It has the weight that pulls directly downward on the box. So that's the weight of the box. However, and that one in this diagram would look like this. But there's another force, which is the normal force. But the normal force in this case is always perpendicular to the surfaces that are in contact with each other. So it's this way, right? This way, like that. And so the normal force would actually point upward in this direction. Right? Now, I've been telling you guys that I like to draw my triangles kind of extremely so that you can tell which angles are which. And so this right here is obviously my smaller angle theta, right? And with my weight, there's also that same idea here. So what we're going to do is we're going to tilt our axes a little bit. So our x is going to be this direction, or we'll call that our parallel direction or our perpendicular direction. We do that, we're tilting our axes. And that means that the normal force is now in the perpendicular direction, but the weight is not. The weight has part of its weight that pushes it into the platform. So that would be the weight in the perpendicular direction. And then part of the weight which tries to make it slide down the platform, which is this one right here. So that's the weight in the parallel direction. This force over here also has a force that is a part of its force which is pushing it up the ramp, which is this force in the parallel direction. And a part of the force which is pushing it into the ramp, which is this force in the perpendicular direction. Now you wouldn't have to do that. You don't necessarily have to do that. In fact, it might be easier to do it the other way. In fact, it's almost guaranteed to be easier the other way. But what you have to know is that you're going to have to break these things down into components somehow. I'll break it down into components the other way too. So if this is our ramp here, and we just leave it in the normal x and y, we just call this x and y. This works too. We'll have a force this direction. We'll have our weight this direction. And then we'll have our normal force, which is going to be pointing up in this direction. And that's fine because the free body diagram will look like this. We'll have a force which is in the negative x direction. We'll have the weight which is in the negative y direction. And then we'll have this normal force which is upward, which obviously has a little bit of positive x to it, the normal in the x direction, and obviously has a lot more y to it, normal in the y direction. And this angle is obviously the theta angle because it's the smaller of the angles. Right? Well, that's obvious to you because your picture is a little bit skewed, but it's obvious to me. So anyway, this works too. But in the end, no matter which way you set up the coordinates and which way you break down the vectors, you're still going to split your things into an x and a y. And we're going to use Newton's second law because Newton's second law says, wait, this one uses a friction coefficient. That's not fair. That's all right. There's also a friction force in this one because it says there is. So there's a friction force in this direction. So there would be another force this way on this thing, this way anyway, frictional force. That one has obviously a negative f sub x and a positive f sub y. But anyway, in the end, what you're going to do is you're going to add all your forces in the y direction, and if this thing is stopped, it has to be equal to 0. If it's moving, if it's accelerating, it has to be equal to mass times acceleration. But it has to be like this. You have to have the sum of all your forces in the x direction, and you have to have the signs correct and cosines of angles and sines of angles, whatever else. But the sum of all your forces in the x direction has to equal the mass of the box times the acceleration in the x direction. And then the sum of all the forces in the y direction has to be the sum of all the masses. Sorry, not the sum of all the masses. The mass of the box times the acceleration in the y direction. There we go. And then you'll get two equations that you'll solve again simultaneously for all the unknowns. And that's the same way we've been doing things all along, is to get as many equations as we can and then solve them for what we don't know. So that's the rough start. Any more questions? Any last questions here before we break for the week? You have any questions, Keegan? All right, so my task for you guys is to get all that reviewing cranked out, go through all those problems that you didn't do so well on, do them again, submit them again, see how you do on them, and get your test scheduled. Get it scheduled at the end of this week or the very beginning of next week, so that when we meet next week, we're starting on new material in the new chapters, and we're moving on and getting done with this class. All right? Have a good weekend.